Hello and welcome to this lecture on the basics of research design. In this lecture, we're going to go over research design in observational and experimental studies. We're going to talk about lots of research design terminology, and we're going to conclude with a discussion of random sampling and random assignment, and how those different types of randomization affect the sorts of conclusions that we can make from our study. Two really important concepts in research design are explanatory variables and response variables. A response variable is also called an outcome variable or a dependent variable. And this is the variable that is the focus of our research question. This is something that we want to explain, that we want to understand better. An explanatory variable, which we also call an independent variable, is something that we use to try to explain changes in the response variable. So we can think of this as an explanatory variable might affect a response variable. So let's say that my research question is, do people who were malnourished as children tend to be shorter than people who were not malnourished as children? In that case, I'm asking about whether malnourishment might affect height. So malnourishment is my explanatory variable, and height is my response variable. Or I could ask, are people who are more wealthy more likely to vote Republican? In that case, my explanatory variable is wealth, and my response variable is voting Republican. Wealth might affect voting Republican. So let's see if you can use this framework to test yourself and see if you understand how we go from a research question to identifying an explanatory variable and a response variable. In this example, our research question is, are citizens in wealthier countries happier on average than citizens in poorer countries? So take a minute, pause the video, and answer for yourself what you think the explanatory variable is and the response variable is. I'll wait. So in this example, the explanatory variable is the wealth of a country, and the response variable is the average happiness of citizens. So again, in this framework we've been talking about, a country's wealth might affect the average happiness of citizens who live in that country. So now that we have this basic terminology down, let's turn our attention to distinguishing between observational studies and experimental studies. Researchers collect data in different ways in observational and experimental studies. In an observational study, researchers collect data by observing the world around them. They don't directly interfere with how the data arise. They don't try to shape outcomes. They just observe. In an experimental study, on the other hand, researchers try to run an actual experiment. They collect participants and they give those participants different treatments to try to understand an outcome that they're interested in. If this doesn't quite make sense, don't worry. We're going to talk a lot about observational and experimental studies throughout this lecture and give lots of different examples. Let's start with the first example now, evaluating this particular research study. In 1979, researchers published an article called Electrical Wiring Configurations and Childhood Cancer. In this study, the researchers wanted to know if being exposed to radiation from electrical power lines was causing cancer, and specifically if it was causing childhood leukemia. So their article reported results from a study that they did in Denver, and their study found that child leukemia rates were higher for children who lived in neighborhoods that were near lots of electric power lines. We're going to talk about the validity of this particular study, but first let's see if we can answer some basic questions about the study. What is the explanatory variable and what is the response variable for this study? Was this an observational study or an experimental study? And finally, what did the study conclude? Take a second and pause the video and answer each of these questions, and then we can move on and talk a little bit more about this study in depth. All right, here are the answers to those questions about this study. The explanatory variable is the child's proximity to power lines. The response variable that we're interested in, the outcome of interest, is childhood leukemia. So we want to know whether proximity to power lines might affect childhood leukemia. This is an observational study. The researchers studied subjects who were living in different neighborhoods in Denver. They didn't try to move people around to different proximities, to different configurations of power lines. They didn't try to find kids who might be particularly prone to leukemia and put them in different positions relative to power lines or anything like that. This wasn't an experimental study. They just observed. And finally, the conclusion that the study came to was that radiation from electric power lines is associated with higher levels of childhood leukemia. When this study came out, it got a lot of attention, which is pretty understandable. It raised a lot of worries for people about whether the electric power lines that they encountered all the time could actually give them cancer. So let's take a minute and delve a little bit deeper into what might actually be behind this association that we see between proximity to power lines and the incidence of childhood leukemia. There are a couple different possible relationships, and I've sort of graphically illustrated them here in this slide. So we might see this relationship between power lines and leukemia because proximity to power lines causes leukemia, which is the conclusion that the authors of that 1979 study thought that they were reaching. Another possibility for why we would see an association between these two variables would be if having childhood leukemia somehow caused a child to live closer to power lines. This is called reverse causality, and it doesn't make a lot of sense in this case, but there are some cases where the reverse causal explanation makes a lot of sense. And another possibility that we need to consider is whether a third factor causes both proximity to power lines and childhood leukemia. Is there another variable out there that is positively related both to proximity to power lines and to the incidence of this childhood cancer? A variable that affects both the explanatory variable and the response variable at the same time is called a confounder. And when a confounder is present, this can make it look like there's a relationship between the explanatory variable and the response variable, when in reality those things aren't related to each other causally at all. So you've probably guessed that there is indeed a confounding variable in play in the study that we've been looking at. In this case, the confounding variable is poverty. Families in poverty are more likely to live in undesirable areas, which include areas with lots of visible overhead power lines. Studies have also shown us that families in poverty are more likely to have children who develop cancer. So in this case, the confounding variable is poverty, which causes both the proximity to power lines as well as the incidence of childhood leukemia. The original study that we're looking at did not take poverty into account, and so it drew this wrong conclusion about the effect of electric power lines. And we've confirmed this with lots of studies since then. Subsequent studies have found no relationship between proximity to power lines and childhood leukemia. In fact, they have found no evidence that radiation from power lines causes cancer of any kind. The lesson we should take from this is that as researchers, we have to be attentive to the possibility that there could be a confounding variable that leads us to see a relationship between an explanatory variable and a response variable when there isn't any real substantive relationship actually there. In observational studies, we can see an association between an explanatory variable and a response variable, but this does not prove that these variables are actually related to each other, and it doesn't prove that one variable causes another. So we can use evidence, this association that we find, to provide support for an idea, a theory, a hypothesis about the actual relationship between the explanatory variable and the response variable. But it's important to keep in mind that observational research cannot prove this, and having good theory is really foundationally important to good observational research. Good theory lets us make compelling arguments about why we see the relationships and associations that we observe. When we do see an association between variables, the main lesson here is that we should always ask ourselves the question, what other factors could be causing this association between variables that I'm observing? So now we're going to switch gears and talk about experimental research design. Let's start by looking at an example. In this scenario, a researcher wants to know if drug A is an effective cure for disease B. So volunteers for this researcher's study get sorted into two groups. Group 1 takes drug A, and Group 2 does not. And at the end of the study, the researcher is going to compare Group 1 and Group 2 to see if people who took the drug are better off and have less instances of disease B than the subjects who did not take the drug. So, again, in our framework of explanatory and response variables, we're wondering if drug A might affect disease B. The explanatory variable is drug A, the response variable is disease B. And we're also going to introduce two new terms. The treatment group is the group which received drug A. This is a treatment that's associated with the explanatory variable, the variable that we want to see the effects of. And the control group is a group that did not receive drug A. And we get to compare the outcomes of the treatment group and the control group to gauge the efficacy of the treatment. Now let's talk about a couple of principles for doing good experimental research. The first of these principles that we're going to talk about is controlling for differences between subjects in the treatment group and people in the control group. Here's a useful way of thinking about it. If I tell you that I had a treatment group and a control group, and at the end of my study, the people in the treatment group were in way better health than the people in my control group, you might initially think that, okay, so whatever treatment I gave to the people in the treatment group was effective. But then if I told you that everybody in my treatment group was 23 years old and everybody in my control group was 83 years old, then you would start to question the validity of my findings. You might say, okay, well, the good health outcomes for the people in the treatment group is because they're younger and have a higher baseline level of health than the people in your control group who are older and more likely to be in failing health. Controlling for differences between subjects in the different groups is a way of avoiding this problem. Essentially, I want to avoid situations where the people in my treatment group look way different from the people in my control group. A useful way of doing this is to randomize subjects into the treatment group and the control group, which is principle 2 that we're talking about here. This means that if I have my pool of potential subjects for my experiment, each of those potential participants has a 50-50 chance of ending up in the treatment group or the control group. So there's nothing about any of those individual participants that makes them more likely to end up in treatment or more likely to end up in control. It's a completely random process. The third principle we're going to talk about is replication. This point is all about making sure that the results of our study are reliable. One way to do this is to do the study with one set of participants, come to our conclusions, and then get a whole new group of new participants, do the same experiment again, draw my conclusions from that study, and then compare them to see if my results across the studies were pretty much the same and my conclusion is the same. If they are the same, that means that my study is well replicable and my findings are reliable. A way of doing this internally in the study is just to have a sufficiently large sample that we can be really confident in our study's results. This should be a pretty intuitive concept. If I tell you that I gave a treatment to 2 people and it was effective for half of those people, that's not going to be as compelling as if I told you that I gave a treatment to 1,000 people and the treatment was effective for half of those people. And the final principle here is blocking. If I think that there is a characteristic of people in my study that might make them more likely to respond differently to the treatment than other people in the study, what I might want to do is what's called blocking them out. For example, let's think about if I know that women and men are likely to respond differently to this drug treatment that I'm giving them. Then what I might want to do is make sure that I split my sample into women and men, and then I can compare the treatment group for women to the control group for women, and the treatment group for men to the control group for men. If the concept of blocking is a bit confusing, your textbook has a really good explanation and some good illustrations of the concept. It's not the easiest thing to describe verbally. Next, we're going to talk about some more experimental design terminology, some definitions that you should know. The first of these is a placebo. A placebo is a fake treatment that you give to subjects in the control group. In medical studies, this is usually something like a sugar pill that people in the control group take, where people in the treatment group take a regular pill with the actual drug in it. The placebo effect is when people in the control group who take the placebo, the fake treatment, actually start to feel better because they believe that they're receiving a treatment, even though they're not. Blinding in an experimental study is when subjects don't know if they're in the treatment group or the control group. This is the main reason that you would give a placebo, is if you didn't want a subject to know if they're getting the treatment or not getting the treatment. If people in the control group were getting no pill, no treatment, no nothing, that would be a pretty good indication that they were in the control group. So we give people in the control group a placebo so that the study is blinded and subjects don't know what group they're in. A double-blinded study is one where both the subjects and the researchers who are working and interacting with those subjects don't know who's in the treatment group and who's in the control group. This is to guard against unconscious biases on the part of researchers. You don't want researchers to unconsciously be treating people in the control group different than people in the treatment group. So we make sure that those researchers don't know which subjects are which. Okay, a couple more research design terms that you should know. A population is all the members of a group which we're interested in studying. So if I have a research question that is about all adults in the United States, that's my population, the adult population of the United States. If I have a research question that is about lake trout, then my population is all lake trout. If I have a research question about countries, then my population is all of the countries in the international system. A sample is a subset of the population that we actually study in a given research project. So, for example, let's say that I want to give a survey to collect data on my population. If I want to study the United States adult population, I'm not going to be able to get my survey into the hands of every adult in the United States. It would cost way too much for me to give out tens of millions of surveys. So what I'm going to do is I'm going to give that survey to some people in the United States. Those people that I give the survey to, that's my sample. Those are the people that I'm actually going to be able to study. And what I hope is that by studying my sample, I'm going to be able to say something about the entire population. A sampling strategy is the way that subjects are chosen from the population to be in the sample. An assignment is what determines whether a subject in my sample is getting a treatment or whether that subject is in a control group. In the experimental setting, the researcher determines who is in the treatment group and who's in the control group, and the researcher can do things like randomize who's in the treatment group and who's in the control group. In an observational study, the researcher doesn't get to determine assignment. So think back to the childhood leukemia study that we were talking about earlier in this video. In that case, the researcher wasn't able to assign who was living in neighborhoods that were near lots of power lines and who was not. That assignment was predetermined, but it was still assignment. It still existed. Treatment groups and control groups still existed, but they were not determined by the researcher. In the last part of this lecture, we're going to talk about random sampling and random assignment and the difference between those two concepts. These are concepts that are going to come up over and over again in this course, so it's important to make sure that we understand them and the difference between them. This is important because whether we have random sampling or not, and whether we have random assignment or not, are things that determine what conclusions we can actually draw from the research that we do. So let's start by considering random sampling. Random sampling means that when I have my population of interest and I'm going to draw a sample out of that population for my particular research study, that when I draw my sample, every member of that population has the same chance of being in my sample as every other member of that population. So there's no group of my population that is more likely to end up in my sample than any other group. So for example, if I want to do a survey and the population that I'm interested in is all Americans in the United States. A bad sampling strategy, if I want a random sample, would be for me to go out on the streets of Columbus and hand out the survey to the first 100 people that I meet and call it a day. This wouldn't be a random sample because this is going to mean that people in Columbus are going to have a much higher probability of being in my study than the rest of the adult population of the United States. So that's not a random sample. I could draw a random sample by getting a gigantic database of phone numbers from people from all over the country, selecting a sample randomly of those phone numbers, and then calling those numbers that were selected randomly and giving those people the survey. That would be one way of getting a random sample of United States adults. If I take a random sample, then the results of the study that I do by looking at that sample are something that I can generalize to the whole population. This is a really powerful effect of random sampling. If I don't take a random sample, then my conclusions are not generalizable to the population that I'm studying, and the best that I can do is make a statement about the association that I found within that sample. So this should make sense. I can't do a survey of only people in Columbus and then say that my results of my survey are applicable and representative of the entire population of U.S. adults. If I want to make a statement about the entire population of U.S. adults, I should be studying a sample of people who are drawn from all over that population, people in Alaska and people in Texas and people in Columbus. Random assignment is a concept that is really important for experimental design, and we actually talked about this a little bit earlier in this lecture. With random assignment, whether a subject ends up in the treatment group or the control group is totally randomized. So every subject in my sample of people that I'm studying has an equal chance of ending up in the treatment group and the control group. This is going to mean that the treatment group and the control group are going to end up looking pretty similar. They're going to have a good random mix of people of different genders, different ages, different ethnicities, all this stuff. So those groups are going to be able to be compared to each other, and differences between those groups are going to be totally random. So let's imagine that I'm thinking about a treatment like a particular exercise regime, and I want to know if people who exercise in this particular way are likely to have better health outcomes than people who don't exercise in this way. If I randomly assign people to treatment and control, then I sort of eliminate differences between those groups. But if I allow people to choose whether they want to be in the treatment group or whether they want to be in the control group, I'm probably going to have systematic differences between the sort of people who say, oh yeah, I want to try that new exercise regime, I want to sort of throw myself into exercising harder or whatever, and the people who say, no, I'm just going to keep doing what I'm doing. Right? So possibly, if I see a difference between the treatment group and the control group in this situation, the differences between the treatment group and the control group are going to be driven by the fact that some people are self-selecting into treatment, and those people are fundamentally different in some way than people who are selecting into the control group. The upshot of this is that if I have good random assignment, then the only real difference between the treatment group and the control group is whether they got the treatment. So this means that I can attribute any difference in outcomes for these two groups to the treatment. I can say that the treatment caused an outcome. This is called causal inference, and it's like the holy grail of statistical studies. Okay, so if I've done a study where I have both drawn a random sample, and then in that sample randomly assigned the subjects to treatment and control, what I end up with is the situation in box 1, where my results I can generalize to the whole population, and I can make a causal statement about the relationship between the treatment and the outcome. This is what's known as an ideal experiment. Below that, in box 3, we have a situation where we didn't take a random sample, but in the sample that we did get, we did randomly assign into treatment and control. You can think of this as being how most experiments are done. For example, on the Ohio State campus, you can sign up to take lots of experiments. and researchers want to get a pool of experimental subjects so that they can do their study. This is not a random sample, right? Most of these researchers are not interested in the population of college students at Ohio State. They're interested in a larger population, like US adults, but they take what's called a convenience sample. They take the subjects that are easy to access, like students on a campus. So it's not a random sample, but it is randomly assigned. And this is going to allow these researchers to make a causal statement about the relationship between treatment and outcome, but only for this particular sample. They can't generalize to the whole population that they're interested in. In box 2 is the situation where we have taken a random sample for our study, but there isn't any random assignment. So because there's no random assignment, this means that we can't make any causal statement about what we find, the association that we find between an explanatory variable and an outcome variable. We can only make a statement about correlation. But because we took a random sample, our conclusions are generalizable to the whole population. So we can say that we see an association between variable x and variable y, and we can conclude that this is something that is happening in the population as a whole. We just can't make a causal statement. A lot of observational studies look like this when the researcher can take a random sample but doesn't have any control over assignment into treatment and control because it's not an experimental setting. And then finally, in box 4, we have the situation where we have neither random sampling nor random assignment. This means that we can't make a causal statement about any association that we find between variables, and we can't generalize to the population. So we can only make a correlational statement about the relationship between variables. We can say those variables are associated within the particular sample that we looked at. So this is sort of not as useful as other types of studies that we can do, not as powerful. It's a pretty limited statement that we can make that we see an association between variables in this particular sample. Okay, and that's the end of our lecture on the basics of research design. As always, if you have any questions, please post on our course discussion board, and I will get back to you as soon as I can. Have a great week.